uh, even and odd functions. Today I'm going to finish up section 3.2. So the rest of the topics that I need to talk about today are the average rate of change, the difference quotient, graphing piecewise functions, and recognizing where functions are increasing, decreasing, and constant. So if we look at this function here, we can tell where it is increasing, decreasing, and constant by reading our graph from left to right. So if I imagine that I have a little person over here, and the person is following this graph, if at the beginning of the graph you can tell that the person is going to have to walk downhill, that is where the function is decreasing. So it is decreasing on the interval from negative infinity to x being negative 2. We always talk about where functions are increasing or decreasing based upon their x values. So I'm going to write this off to the side. Decreasing. And I'm going to write the intervals where it's decreasing. The first interval is from negative infinity to negative 2. And again, we're talking about x values here. Then, once our person, here I'm going to get rid of these little lines that keep moving around when I move this person. When the person gets down to the bottom, oh, I'm still writing, not good. When this person gets down to the bottom here, at x equals negative 2, he's going to have to start climbing until he hits x equals negative 1. So in this interval, our function's increasing. I'm going to write that down off to the side over here. We're going to start summarizing where our function is increasing, decreasing, and constant. So we are increasing from negative 2 to negative 1. Now at this point, our person is standing here and they are going to walk without going uphill or downhill from negative 1 over to x equals 0. So at that point, our function is constant. And again, that's from negative 1 to 0. And I think I'm going to move this over because I'm going to run out of room. And now we get over to where x is 0, and our person is now moving downhill. So between 0 and x equals 2, our function is decreasing. And then again, our person is going to have to climb from 2 until x equals, wow, that says 0, 4. Not likely. I bet, let's change the ordered pair here. We're going to make this, let's make it 5, 4. Okay, so we are going to be increasing again from 2 to 5. And then, after that point, our person is going to have to walk downhill. So after our person gets to x equals 5, it's all downhill from there. And I'm going to add that interval on here. From 5 to infinity. So we can see, just by reading our graph from left to right, where we are decreasing, increasing, and constant. And that's all there is to that. The next thing I want to talk about is the average rate of change. The average rate of change is actually the slope of the secant line through 2 points on our curve. So if I look at 2 points, one for x1 comma fx of 1, and x2 comma fx of 2, and I figure out the slope between those 2 points, that's my average rate of change. So the difference in my y's over the difference in my x's. You might want to pause the video and copy that formula down. So let's do an example. we're going to find the average rate of change of k of x, our function here, from x equals negative 1 to x equals 2. So we're going to go with our formula. Again, it's the change in y's over change in x's. So k of x of 2 minus k x of 1 over x2 minus x1. So we're going to substitute in. I'm going to let my x1 be negative 1, and my x2 be positive 2. So my average rate of change is k of 2 minus k of negative 1, and that's all going to be over 2 minus a negative 1. So we're going to evaluate k of 2. Well, k of 2 is, I'm going to write this here, 2 to the 4th power, which is 16. K of negative 1 is going to be negative 1 to the 4th power, which is just 1. So we're going to plug in down here. We have 16 minus 1 all over 2 minus a negative 1, which is 3. So that becomes 15 over 3, or 5. So my average rate of change between x equals negative 1 and x equals positive 2 is just 5. Again, that's the slope of my secant line between x equals negative 1 and x equals positive 2. The next thing I'm going to talk about is the difference quotient. The difference quotient is really exactly the same as average rate of change, only it's a little bit different of a way of looking at it. Instead of looking at an x1 and an x2, I'm going to look at an x1 and then an x plus h. So h is going to be the width of where I'm looking. Actually, it's the difference in my x's that are going to go in my denominator. So we're going to do an example like this where we evaluate the difference quotient. And later on in calculus, what you're going to see is we are going to be able to figure out what the slope of that secant line is at any point on our curve. So let's evaluate the difference quotient here. It's going to be f of x plus h minus f of x all over h. So we'll plug into our function. We'll get f of x plus h is 2 times the quantity x plus h squared plus 1 minus f of x minus 2x squared plus 1. That's all going to be over h. So let's simplify. So I'm going to multiply out x plus h quantity squared, 2 times x squared plus 2xh plus h squared plus 1 minus, let's distribute the negative, 2x squared minus 1, again, all over h. I'm going to make this a little bit smaller so I have some more room. Let's see here. Nope, don't want to move that. Let's group this and make it a little bit smaller. That might be a little small. Put this off to the side. All right, now we are going to distribute the 2. So that gives me 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1 all over h. All right, now we're going to combine some like terms. We have a plus 1 here and a minus 1 there. Those are going to cancel out. I have a 2x squared here and a minus 2x squared over here. Those are going to cancel out. So then I'm going to be left with, let's see if I can move this down a little bit. Yeah, here we go. We're going to be left with 4xh plus 2h squared all over h. Well, I'm going to be able to factor an h out of my numerator. So h times the quantity 4x plus 2h all over h. Those are going to cancel out. And I'm going to find that my difference quotient is 4x plus 2h, which is really good to know because as h gets smaller and smaller and smaller, I'm going to go back to this last page. Let's see if I can do this here. Let's make a dual page display. As h gets smaller and smaller, the width gets smaller, the difference between my x's gets smaller. My secant line is going to get closer and closer to be a tangent line at one point on this curve. So as h goes to 0, and this is what you're going to find out in calculus, as h goes to 0, we call that a limit. As the limit of h goes to 0, as the limit of my difference quotient, as h goes to 0, I can't get this out right. Let's do it one more time. I'm going to actually write this down. As the limit as h goes to 0 of f of, let's write just difference quotient. So I'm not, no, I guess I'll write that down. F of x plus h minus f of x all over h. So when I look at this quantity, as h goes to 0, what I'm going to come up with is the slope of my tangent line. And this is going forward a little bit to what you're going to see in calculus. But if I look at this, what I'm going to find is the slope of my tangent line at any point x is 4x, because that's what happens when h is 0. And that's really part of what you're going to find out in calculus. So a little preview for you. But for right now, what I really want you to be able to do is evaluate the difference quotient. Okay, let's go back to my single display. Next, piecewise functions. With piecewise functions, the only thing that you're doing, you're graphing these two graphs only in specified domains. So when x is less than 0, I'm going to graph h of x equals x squared. But as soon as x becomes greater than or equal to 0, I'm going to graph x minus 1. So we're going to plot along here. If you recall, h of x is x squared. That's a parabola. So at x equals 0, h of 0 is 0. Now let's do this. When x is less than 0, I know h of x is equal to x squared. So let's start this way. When x is negative 1, h of x is 1. So I'm going to plot that right there. When x is negative 2, h of x is 4. I'm going to plot that here. When x is negative 3, h of x is 9. I'm going to plot that here. And we see the left part of the parabola. Now, what's going to happen is, right at this spot, we're going to have an open circle because we want to graph everything to the left of x equals 0, but not including 0. So I'm going to connect these points, like so. And now, at x equals 0, I'm going to start graphing this part. So we're going to put in, let's see, well, we're going to make a new t-chart. At x equals 0, now I'm plugging into the second part of my piecewise function. H of x is equal to negative 1. At x equals 1, h of x is going to be 0. And you can see this part of my graph is going to be a line. So I'm going to plot some points. At x equals 0, h of x is negative 1. That's a closed circle there. So my graph is actually going to hop. As soon as it gets to x equals 0, it's going to hop over to x equals negative 1. Then at x equals 1, my function is going to be 1. And then I'm going to have basically a line here with slope 1 and y-intercept 1. And I think I'm going to use my line tool because that'll make it easier for me. So my line is going to look like so. I think I got it. Yep. Okay, and that's what my piecewise graph looks like. If I want to write the intervals where my function is decreasing, increasing, and constant, I would say that it's increasing on the range negative infinity, actually on the domain, negative infinity to 0, and it is increasing, ooh, I meant decreasing, hold on, let's rewrite that. Oh, didn't mean to go back that far. There's my line. Okay, so it is decreasing from negative infinity to 0, and it is increasing from 0 to positive infinity. Notice it is not constant anywhere on this graph. Now, greatest integer function. Saw a little bit of this last year. The greatest integer function is represented with this kind of notation, and it stands for the greatest integer less than or equal to x. So if you look at the function below, if x is 0, my function is 0, because 0 is less than or equal to that. If x is a half, f of x is still 0, because the greatest integer less than or equal to a half is 0. But as soon as x is equal to 1, it's going to jump up here. And I actually have a step function, and it's going to look just like that. And there are some other common functions that you should be aware of, and they are on page 257. I've actually copied a picture of this into my notes. And here they are, but you're going to want to pull your book out because this is really tiny looking. We have a linear function, and that's just the equation of a line. It is neither odd nor even. We have a constant function. Our constant function looks like so. It is even, it is symmetric over the y-axis. Our identity function is y equals x. See this here? And it is just this main diagonal, and it's odd, it's symmetric over the origin. We have a square function, which is really a parabola, and that looks like this, it's even. And you can see the domain of this is from negative infinity to positive infinity, but the range is from 0 to positive infinity. You can see that here. If you look back, my linear function, the range and the domain are both negative infinity to infinity. My constant function, the domain is negative infinity to infinity, but the range is just simply that constant. The only y value that gets mapped to is my constant. When I look at a cubic function, looks like so. It is odd, it's symmetric over the origin, and my domain and my range are negative infinity to infinity. Square root function looks like this. It is neither odd nor even, and my domain and range are both 0 to infinity. The cube root looks like this, and the domain is from negative infinity to infinity, and so is the range. And it is odd. Notice it's symmetric over the origin. Then we have absolute value, and that looks like a V. My domain is from negative infinity to infinity, but my range is only from 0 to infinity, and it is even. I have the reciprocal function. It looks like this. And actually, this is a hyperbola, only it is rotated 45 degrees. Just something worth knowing, but it's really a reciprocal function. And my domain goes from negative infinity to 0, and 0 to infinity because I have a nice vertical asymptote at that y-axis. And my range goes from negative infinity to 0 and 0 to positive infinity. I want to make sure that I stated this right. My domain goes from negative infinity to 0 and 0 to positive infinity because I have a vertical asymptote that runs through my y-axis. My range, I have a horizontal asymptote that is my x-axis. That's why 0 is excluded. And this is odd. You'll notice it's symmetric over the origin. And that covers everything from section 3.2. So take a look at Schoology, see what the homework assignment is, and get started.